All right. Morning, everybody. Sorry about yesterday. My watch stopped and then I kind of lost track of time. So let me go ahead and get started with that. So sorry about the video going a little bit longer yesterday. So let me go ahead and let me start the time there. So that way, then I don't overshoot my time too much. But no emails so far, so no questions. I've noticed that only a few of you have been watching the videos. Again, the videos I won't. They're not due. If you look on Classroom, not due till next Friday. Next Friday, the 8th. Yeah. So, but I wouldn't. Again, please make sure you try to watch the videos. Spread them out a little bit. Don't try to watch them all in a couple sittings. It'll just make your mind numb, you guys. It won't benefit you on that one. Okay, so please make sure that you keep up with the videos and ask your questions. Email me the questions, and I will go ahead then and I will address them in the next video. But like I said, today no video, no questions. Again, no questions. So like I said, please keep up. I've suggested, if you look on Classroom today, I have posted set A and set B. Again, I'm not requiring that you turn them in. I just require that you watch the videos and submit the work based on the videos. But do try set A and set B from chapter 14. It'll help you kind of review what we've talked about up to this point. Okay. All right. So we left off. So let's go ahead. Let's pick up where we left off with yesterday. And we were talking about this reaction here. So let me go ahead and let me share this screen with you. Okay, let me share my screen with you. And we were talking about this generic reaction here, where we have then a generic acid. Okay, generic acid. The acid here is the acid HA. Okay, and so with that said, then this acid, we can define this acid in terms of the Arrhenius acid base theory, because remember, with the Arrhenius acid base theory, basically he just stipulates then that any compound that can produce an ionizable hydrogen. And if we're talking about this as an acid, we're talking about HA as an acid, what we were saying then, according to the Arrhenius acid base theory, is that this equilibrium is happening here, where this particular compound breaks up into these two components here. You have then the hydrogen ion and the appropriate anion there. Okay, so this is how Arrhenius defines Arrhenius defines then an acid. An acid is any compound that can produce an ionizable hydrogen, a hydrogen ion. That's essentially what he's saying. Okay. All right. Bronsted-Lowry, on the other hand, defined an acid based on what it does when that particular compound finds another compound. So in this particular example here, if you take a look at this, this is an acid because what it does is it gives its hydrogen. So if we trace the arrows here, okay, what it does is it gives its hydrogen to water. Okay? And so when it gives its hydrogen to water, we form this particular compound here, this ion here, which we refer to as the hydronium ion. Okay, this hydronium ion, and we were left then with this particular anion here. Okay, so this is why when we take a look at this compound here, it is also an acid according to the Bronsted-Lowry acid-base theory, because in this particular definition of an acid, it donates the hydrogen. So therefore, if hydrogen here, if HA here is the acid, this must be the base according to the Bronsted-Lowry acid-base theory. Because remember, with the base, Bronsted-Lowry base, it is any compound. They define it as any compound that can accept a hydrogen ion. Okay, so a hydrogen ion acceptor is what we refer to as a base. A hydrogen ion donor is your acid. Okay, and so with that said, then that's going in the forward direction, towards the right. Okay? But this reaction is at equilibrium. That's what these two arrows mean, which means then the reverse reaction starts to happen as well. And in this reverse reaction, we can also define the two components of that reverse reaction as an acid or a base based on whether it's donating or accepting hydrogen. Okay? So therefore, in the reverse direction, this hydronium ion ends up being the acid because it's going to give its hydrogen back to the anion here. And so therefore, that's why this is considered an acid. However, since we already have an acid here, we refer to this acid, the acid in the reverse direction, as the conjugate acid. Okay? It is the conjugate acid, meaning that it is the acid that goes along with this base right here. Okay? And so therefore, if this compound then, according to the Bronsted-Lowry acid-base theory, is going to accept a hydrogen ion from the hydronium, this makes then the anion here a base, And since we already have the initial base here, the base in the reverse reaction and the reverse direction, we refer to as the conjugate base. Okay, all right. So according to the Bronsted-Lowry acid-base theory, then, an acid is any compound that can donate a hydrogen ion. A base then is any compound that can accept a hydrogen ion. In that case, then what we do is we have broadened the definition of what an acid and a base, what acids and bases are. Okay? All right. So that's a quick review of what we did up to this point. Okay. And then what we did yesterday then is we took this reaction, and this is what's known as an ionization reaction, because what we have here is that we're forming these two ions here. Okay. So when we write out these ions, and we practiced that yesterday, once we write out these ionization reactions, then we can then write out, since this is at equilibrium, we can write out the equilibrium constant for this particular reaction, which we refer to with the subscript A as the acid dissociation constant, because what's happening here is the acid is breaking up. It is dissociating. It's interacting with water, and it's dissociating. Okay. All right, so we can write then the law of mass action for this particular reaction here, okay, which we have done before. But then we have then hydronium ion in the numerator, okay, along with the conjugate base in the numerator, and then the undissociated acid in the denominator. Okay? And so we leave water out. We leave water out, remember, because this is a pure liquid. Okay? So this is the equilibrium constant for this particular reaction. And that's how we write it. And we did that yesterday. Okay? Now, what we're going to do today then is we want to be able to use, so if we are given the concentrations of the hydronium ion, the conjugate base, the undissociated acid to start out with, we should be able to calculate for Ka. Okay. What we want to be able to do today is how are we going to interpret Ka? Okay. So how can we interpret Ka to determine, for example, which side is favored during the course of this ionization reaction? We want to interpret Ka in terms so that we can determine then whether the acid is a strong acid or a weak acid. Okay. And so with that said, then let's go ahead and do that. Okay. So when we talk about strong acids, we already did this before. So let's go ahead and let's deal with that point. Okay. Let's remember what strong acids are. Okay, so a strong acid, remember, so we defined a strong acid as an acid, and remember we had that list of acids that I gave you. A strong acid is an acid that dissociates completely, complete dissociation. That means then it breaks up completely, dissociation. That means that it breaks up completely. So we can imagine then an example of a strong acid. Our acid here, if this was the acid, it would break up completely. So you have hydrogen ions and the anion only, okay, with very little of the reverse reaction occurring because we have complete dissociation. We almost say nearly, almost 100%. Now, obviously, we would never get 100%, but the strong acids then, and you have a list of them, and if you want me to, I can repost them again for you, but they almost dissociate completely. Okay, so complete dissociation, which means then the right-hand side, the product side is favored in this particular process here. Okay, so if you can imagine then, if that is the case, we look at Ka here, so let's go ahead and use our expression, our law of mass action here to interpret this. Okay, so if we take a look at this, then, if for strong acids, can you imagine this, that the product side here would be favored? It would be much bigger than the reactant side, which means then the numerator here will be much greater than the denominator. Therefore, when we talk about strong acids, okay, we expect then the strong acids to have a Ka that is large. Large Ka. Okay. That is very large. Okay. So the bigger the Ka, okay, the stronger the acid. So the Ka for strong acid should be very big. It should be a very big number. Okay. All right. So if that's what we know then for strong acids, let's go ahead and take a look at what the weak acids are. So for weak acids, okay, let me go ahead and do this again. Okay, so for weak acids, remember we said then that they don't dissociate completely. We have incomplete dissociation. So let's go ahead and do this. So for weak acids, we define a weak acid as any acid that has incomplete dissociation. So we have incomplete dissociation. Okay, Which means then that when we take a look at the reaction, what that means then is that the reverse reaction here, and the equilibrium, okay, so when we take a look at that reaction there, okay, it's the reverse process that will dominate. That means then we have more undissociated acid. We have more undissociated acid than when it dissociates. Okay, so that means we still have a lot of this left over. Okay, so looking at our reaction here then, and looking at how Ka works out, that means that if for weak acid, if we have very little product and a whole lot of reactant still left over, our denominator will be bigger than our numerator. And so what is the consequence for that when we look at our Ka? The Ka then should be very small. Okay, so for a weak acid, the Ka should be small. For a strong acid, the Ka should be very large. Now remember, strong and weak does not refer to concentrations. Strong and weak, the term strong and weak acids refer to how much the acid dissociates. Okay? Concentration then is not how we define strong and weak. The strength of an acid is based upon how much it dissociates, not how concentrated it is. Okay? All right, so this is what you folks have to remember. This is how we can use our Ka to determine the strength of an acid. Okay? So a strong acid will have a very large Ka. It will dissociate completely. A weak acid would have a very small Ka, and you would have very little dissociation. We would not have that much dissociation at all. Okay, so we have very little dissociation involved with that. Okay, so let me go ahead. So please make sure you keep that in mind as we move forward with this. Okay. All right, so summarizing what we've talked about here then. Okay, summarizing what we've talked about here. Whoops, sorry. Okay. So for strong acids, the ionization then the ionization reaction, the equilibrium is going to be far to the right, meaning then the products are favored. And if the products are favored in this particular process, then it's going to have a Ka that we said then is going to be very large. You're going to have then a large Ka, and make sure you keep this in mind. For strong acids, you will have a large Ka. Okay. The bigger the Ka, the stronger the acid. Okay. Which means then, what does that mean for our conjugate base here? What that means then for the conjugate base is, since the reverse reaction is not going to happen as readily, the reverse reaction does not take place very much. Okay? That means then this base here, the conjugate base here, is not going to be very good at picking up this hydrogen here. It does not want that hydrogen because the reverse reaction doesn't happen that much. Remember, for the reverse reaction to happen, the conjugate base has to accept a hydrogen from the hydronium here to go backwards. So for strong acids, that is acids with a very large Ka, what that means for us then is that the base here, so remember the conjugate base here is not going to be very strong. Okay, it's going to be a weak conjugate base compared to this base here. Okay, so the base that you start out with, in this case it's water, will be better at picking up a hydrogen than the conjugate base. Remember, a base is any compound that will accept a hydrogen. Now we can assess the strength of the bases as well. Okay? Because if the base on the right for a strong acid, if the base here is not very strong, it's not going to pick up a hydrogen from this hydronium ion. Okay? It's not going to be as good at doing that as the base that we started out with here. Okay? So make sure you keep that in mind. That's what it means then by a weak conjugate base. Okay? So with that said then, on the flip side, okay, if we take a look at the weak acids then, we said then that with the weak acids, the Ka then is going to be a small Ka. You're going to have a small Ka for weak acids. Okay? And what that means then is that the equilibrium is going to favor the left-hand side. That's what it means by having a small Ka. Okay, so with that said, what that means then is that the reverse reaction is going to be favored, which means then this base here now, the conjugate base, is going to be stronger than the base that we started out with. Okay? So that's how we can assess the strength of the base as well for weak acids. Okay. All right. So the general rule that we can use. Okay. So let's go ahead and let me go ahead and say this. Let's take a look at a table of weak acid, the Ka then. Okay. So these are the strong acids here. I already gave those to you. Okay. If it's not on this list, okay, and the list I gave you, I think has a couple more, but basically these are the more commonly found, commonly used strong acids. Okay? If they're not on this list, they will be considered weak acids. If you need to, have me post it again for you, go ahead and just email me. But if you look on the text, if you look on the email, our classroom stream, you should probably be able to find this. Okay? So these are the list of the strong acids, which means then the Kas for these will be very large. So for example, the Ka for hydrochloric acid, and I'm just going to give you this number as a point of comparison. The Ka for hydrochloric acid on the order, so the Ka for hydrochloric acid on the order of 1 times 10 to the 6. Okay? So 1 times 10 to the 6 is the Ka for hydrochloric acid. Okay? And so with that said, you're going to see in the next list then that the when you compare the Kas with the Kas of the weak acids, this is a huge number. So the order of on the order of 10 to the 6, that's a million. Okay? All right, so let's go ahead then. So again, on this list here, if it's not on this list, then it will be a weak acid. Okay? So if you take a look at this list here, look, folks, okay? These are Ka values for the weak acids. And well, here we have then, let me go ahead. There's acetic acid. We've talked about acetic acid so far. Take a look at hydrocyanic acid here. And so if you take a look at these here, hydrofluoric acid, these are all weak acids. Look at their Ka values. Okay? So the strength of the acid increases as we go up. Why? Because look at the Kas. The Kas get larger and larger as we go up. Okay? And so the strongest of these acids on this list here is the hydrogen sulfate ion. Okay? It is an acid because it's possible that this this particular compound here can donate its hydrogen ion. It has a hydrogen ion that can donate. So it has a Ka value of 1 times 10 to the minus 2. Okay? So this is the strongest acid on this list here as a weak acid. Okay? Compare that, you guys, to the one I just gave you for hydrochloric acid. Okay? So I gave you HCl, okay? And I said then that the Ka for HCl is on the order, the coefficient I can't remember off the top of my head, but it's on the order of 10 to the 6th. Okay? Much, much greater than this, which means then this acid here almost completely dissociates. That means it breaks up completely into hydrogen ions and chloride ions. Okay? Whereas these here on the bottom, they don't. They would prefer to stay intact. They would prefer to stay in the way that we see them right now. Okay? And so that's how we can use the Kas in order to determine the strength of any type of acid, okay? Strength of any type of acid. All right. So looking at this graphic here, this is what we see. The strong acid then, when the strong acid, so our generic strong acid here with a hydrogen ion, with the silver sphere here, and the anion, which is the green sphere here. For a strong acid, then what happens for this binary acid here, what we see then is that it breaks up completely into the hydrogen ion and the anion itself. Okay, so we have an equal mixture of both because this is a 1-to-1 ratio. Obviously, if this was a 2-to-1 ratio, then this would change. But you have then a 1-to-1 ratio here. You have equal proportions of both the hydrogen ion and the anion itself because we have complete dissociation here. That means then what we started out as together, we have nothing left here. It is separated into the separate ions themselves. Okay, that's why the spheres are separated here. Okay, so that's for the strong acid. Compare that to the weak acid here. Okay, so another we have another binary acid here, but it is a weak acid. Okay, made up of the hydrogen ion and now the new anion here. When a weak acid dissociates, now understand dissociation has to occur. That is, the process of breaking up has to occur, but it doesn't break up as much. So I want to point out to you this fact right here. If you notice then, we still have, so there it is, there's the hydrogen ion there, okay? And we have the anion there, we have them, it does break up. However, if you look at this here, the majority of what's left over after the process is the undissociated acid. This is the undissociated acid, which means then it doesn't break up. And if you notice, that is actually the dominant species after the reaction has occurred. So if you take a look at the graph here, if you look at the bar graph, here you start out with only the weak acid. It starts to dissociate. So it does start. So it has to dissociate or else it can't be an acid, but we don't have that much of it. We have a whole lot more of the undissociated acid. And this is the characteristic of a weak acid. More, a very little dissociation, okay? A lot of the undissociated acid, and that's what characterizes a weak acid. Okay? So very little dissociation. All right. So to sum up here what we've talked about, okay, we have then the strong and weak acids. We have then Ka is going to be very large. Use this table to help you guys. Use this table to help you review what we've talked about here, okay? And so if you have any questions about this, please make sure you email me. But again, just to quickly review, strong acids, Ka is large, weak acid Ka is small. That means in the dissociation for the strong acid favors the product. The dissociation at equilibrium for weak acids favors the reactant. That's what it means. So far to the right, far to the left. Okay? Which means in the concentration of the hydrogen ion is almost going to be the same, and you saw that in the previous graphic, as the starting concentration of the undissociated acid itself. And that's what it means here. Okay, so HA initial here means the initial concentration of the undissociated acid, which is almost going to be equal to the concentration of the hydrogen ion. And I will add to here also that it is also going to be almost equal to the concentration of the anion as well, the conjugate base. Okay, so all that is true as well. However, with the weak acid, then the initial concentration of the undissociated acid is going to be much, much greater than the concentration of hydrogen ion, which is going to be almost equivalent to the concentration of the anion itself. Okay, again, this is a 1-to-1 ratio here when you make sure you keep that in mind. And then finally, for the conjugate base of a strong acid, it's going to be much weaker than what we started out with in this sampler. Then it's going to be water. And then for the weak acid, the conjugate base for the weak acid then is going to be much conjugate acid for the conjugate base for a strong acid is going to be much weaker than water, and the conjugate base for a weak acid is going to be much stronger than the base that we started out with, okay? Which in this case will be water. Okay? There is a general rule that we can use, but you got to be careful about this. Okay? The general rule that we can use here, and that basically states this: okay? The conjugate base for a weak acid, okay, the stronger the acid, okay, the weaker its conjugate base. Okay, the weaker the acid, the stronger its conjugate base. Okay, so strong acid will produce a weak conjugate base. Okay, and a weak acid will produce a strong conjugate base. Okay. So that's a general rule that you can use. I would use this cautiously. Okay, I would use this very cautiously, but it's a general rule that does work many times. Okay, so the conjugate base of a weak acid is going to be strong. The conjugate base of a strong acid is going to be weak. So you kind of think of it in terms of the opposite there. Okay, so you want to make sure you keep that in mind. Again, I would caution its use. Okay, and we're gonna I'm gonna point that out to you in just a moment. Okay, when we work through some of these problems here. Okay, so let me go ahead and save that for us. Okay. All right. So with that said, then I want to let's talk about real quick then I want to talk about how we can calculate acid strength and acid and base strength. I want to talk about that in just a moment. But in order to do that, we have to talk about this process right here. Process that you see on the screen right here, which is what we refer to as the auto-ionization of water. What does this mean then? Water we don't typically think of as an acid or a base. We think of it as neutral. It's neither an acid nor a base. Okay, that's how we typically think of water. That's how we learned about water as we back in first year chemistry and back when you first took chemistry in junior high. Okay? All right. However, now that we know about the Bronsted-Lowry acid-base theory, okay, we can talk about this property of water that we refer to as auto-ionization. It auto-ionizes, okay, which means then water reacts with other water molecules. Okay? So let's imagine this happening here, guys. Let's imagine this happening here. We have two water molecules here. Okay? What happens then is this water molecule here takes its hydrogen ion, takes this hydrogen ion here, it takes this hydrogen ion here, and it will donate it to this water. Okay, so it donates it to that water. So if you notice, if this hydrogen ion, if this water molecule does that, okay, in donating its hydrogen ion, this now then is our acid. According to the Bronsted-Lowry acid-base theory, this water molecule is going to be the acid, and this water molecule will be the base. Okay? All right. So in donating this hydrogen ion, this hydrogen atom to this water molecule, we form then a hydronium ion. Here it is. There's our hydronium ion. Hydronium ion. Okay. Okay. And here, this is the hydroxide ion. Okay. We form then 2 new ions because of that. Okay. All right. And so if we take a look at this, this then would be our conjugate. This is our conjugate acid. And this would be our conjugate base. Okay. So water does this. This is why water then has, when it auto-ionizes, it will produce then this acid and this base here. Okay. Now, make sure you understand, and we can actually write this. We can write this in a simpler manner here. We typically, so this is the auto-ionization of water. We can typically write the auto-ionization of water in this way here, where we say then that water will break up into the proton and the hydroxide ion. Okay, so that's what we can do right there. We can write it out that way. Okay, now with that said, then okay. We should be able to write out the K equilibrium constant expression for, so if this reaction does occur, we should be able to write out the expression for this, the value, the equilibrium expression for this one here. And let's go ahead and do that. Okay, so let's write out, let's write out the equilibrium constant for the auto-ionization of water. And I'm going to go ahead then, and I'm going to use this here. Okay, so we can go ahead and we can simplify the auto-ionization of water by writing it this ways. Okay. Whoops, sorry. We can do it this ways. We can write it out this ways right here. Whoops. Okay. And I'm going to go ahead then. I'm going to write it out. Write out the equilibrium constant expression using this bottom reaction. Okay. So with that said, then we have then the concentration of hydrogen ion times the concentration of hydroxide ion. And that is it. Why? Again, make sure you keep this in mind. This is liquid water here. This is in water, so that's aqueous, and this is also aqueous. Remember, pure liquids are not included in the equilibrium constant expression. Okay, so the equilibrium constant, the law of mass action, the equilibrium constant expression for this process for the auto-ionization of water is this one here. This is a special constant as well. We refer to this one as Kw, and you probably learned it in first year chemistry already. So this is what Kw is. Kw then represents the auto-ionization of water. And it's an equilibrium constant. You didn't learn about you didn't learn that back in first year chemistry, but now you do. It's an equilibrium constant. And we know then that this number is special. This is special because it is a constant number as well. This is equal to 1 times 10 to the minus 14. Okay? So the equilibrium constant for that one is going to be equal to 1 times 10 to the minus 14 at a temperature, and what you got to make sure you keep this in mind, at a temperature of 25 degrees Celsius. Okay? So this expression here, okay, is what we refer to as the auto-ionization of water. Okay, so this is the equilibrium constant for the dissociation of water. Okay, so that's what we refer to as Kw, and Kw is a constant number. It is equal to 10 times 1 times 10 to the minus 14. Okay, so this is always going to be constant as long as the temperature is at 25 degrees Celsius. Remember, we talked about this equilibrium constants are dependent on the temperature, and that holds true for Kw as well. Okay, so Kw then is the equilibrium constant for the auto-ionization of water. Okay? All right, so water does this. Okay, so water does this, and so when you take a look at the product of these two here, they will always be equal to 10 to the minus 14. Okay, and so make sure you keep that in mind. All right. So why are we talking about this then? Okay, why are we referring to this? Because what we can do with this then is that if we can do this and we have the concentrations, okay, and we can define the two concentrations, or if we can measure, for example, the concentration of one of these ions here, we can determine then the concentration of the other. And based on that, we can we can define then the strength of that particular acid or base. Okay, so let's go ahead and let's talk about this here. Okay. All right. So sorry, guys. All right. So water then is based on what we just saw. Then that water can behave as an acid or base. We just saw that. Okay. That's what we refer to as an amphoteric compound. Water is an amphoteric compound. I mentioned this for you already. Being an amphoteric compound means then that that particular compound can be an acid or a base. We saw then with the autoionization of water, one water molecule acts as an acid and the other water molecule acts as a base. Okay? And so there are other amphoteric compounds as well. For example, the hydrogen sulfate ion is an amphoteric compound, and we talked about this. Okay? And so, but water then is the most common amphoteric substance compound that we come across. Okay? All right, so with that said, then at 25 degrees Celsius, we know then that this has to be true. So if this has to be true, the concentration of hydrogen ions and the concentration of hydroxide ions, okay, will at 25 degrees Celsius will be equal to times 10 to the minus 7. Okay? And so with that said, then if during the course of the autoionization of water, okay, if the concentration of these two have to be equal, because we saw then with autoionization water, it was a 1 to 1 to 1 mole ratio. Okay, so the concentrations should have to be equal. Therefore, the concentrations will be 10 to the minus 7. So that's how we get this constant here. Okay, now what you need to make sure you keep that in mind then, that the concentrations here can change. How do they change? If we add in more hydrogen ions, obviously we will change the concentration of hydrogen ions. Okay? And if we add in more hydroxide ions, we will change the concentration of hydroxide ions. However, the equilibrium constant here will not change. Okay? So therefore, if you add in more hydrogen ions, what has to happen? You're gonna have to decrease the amount of hydroxide. How that happens, we'll talk about in just a moment. Okay? But make sure you keep this in mind then, that though these concentrations are equal when the water is neutral. Okay, so this is always going to be true for neutral water. So when we are at neutral, and we'll talk much more about that in just a moment. Okay, so when we are at a neutral state, we have the equal concentrations of hydrogen ions and hydroxide ions, and we see that. However, we can change the concentrations one or the other, but as one changes, the other one has to change as well, because this has to be constant. Okay, so at 25 degrees Celsius, the equilibrium constant for water has to always be 1 times 10 to the minus 14. Okay, so how then can we use this to our advantage, folks? How can we use this to our advantage? Okay, well, let's take a look at this here. Okay, so at 25 degrees Celsius, okay, we have this, okay, and this is the equilibrium constant here. Okay, so if these two concentrations are equal, if those two concentrations are equal, it should be pretty straightforward. Then we have a neutral solution. We have an equal amount of hydrogen ions and hydroxide ions. Okay? That's neutral. So if you take a pH meter, for example, you put it into a clear solution of water, and you end up with a hydrogen ion that is a hydrogen ion concentration that is 10 to the minus 7, you'll know what the hydroxide ion concentration is. That'll be 10 to the minus 7. Why? Because this has to always be 1 times 10 to the minus 14. And once these two are equal, you have a neutral solution. However, what if you have a solution in which the hydrogen ion concentration is greater than the hydroxide ion concentration? In that case, then you have an acid solution. What that means then is that the hydrogen ion concentration is going to be greater than 10 to the minus 7. Okay? And so make sure you keep this in mind. So at this point here, okay, these two here, and let me go ahead and write this in, and just as a note here. In this case here, then the hydrogen ion concentration is going to be equal to the hydroxide ion concentration, which has to be equal to then 1 times 10 to the minus 7 molar. We already saw that. I gave that to you in the previous slide. Okay. For an acid solution then, what we're going to see then is that the hydrogen ion concentration has to be greater than 1 times 10 to the minus 7 molar. Okay. Because if they're equal, then the only way that we can have an acid solution is that we have a hydrogen ion concentration that's going to be greater than 10 to the minus 7, which means then the hydroxide ion concentration, and let me go ahead and write this in here, the hydroxide ion concentration then has to be less than 1 times 10 to the minus 7 molar. And this has to be true for an acid solution. Okay? So with the base solution then, we see then, I think you can draw the conclusion then. With the base solution then, the hydroxide ion concentration is going to be greater than the hydrogen ion concentration, which means then, okay, we have then the hydroxide ion concentration will be greater than 1 times 10 to the minus 7 molar. And the hydrogen ion concentration in these solutions will be less than 1 times 10 to the minus 7 molar. Okay? And so if you keep these values in mind here, and you can compare them, okay? So for a neutral solution, both have to be equal to the 1 times 10 to the minus 7. Okay? For hydrogen ion concentration then, for an acid solution then, hydrogen ion concentration will be greater than 10 to the minus 7 molar. The hydroxide ion concentration will be less. Okay? And for a base solution then, okay, the hydroxide ion concentration will be greater than 10 to the minus 7, and the hydrogen ion concentration will be less. You only need to measure one of these. You don't have to measure both. And we typically measure the hydrogen ion concentration. We typically don't measure the hydroxide ion concentration. We can measure the hydrogen ion concentration with the pH meter. We can measure with the acid-base strips. Okay, so we can measure the hydrogen ion concentration, and based upon these summaries here, based upon what I've given you here, we can then go ahead and determine whether the solution is an acid solution, a base solution, or a neutral solution. Okay, so that's what we want to be able to use the autoionization of water for. That's how we want to be able to use Kw, okay, which is the equilibrium constant for the autoionization of water. Okay? All right. Any quick questions? Oh, I'm sorry. If you have questions on this, please make sure you write this down, and that way then email it to me, and then I will address you. I will address it. Yeah, I'm sorry. I'm still in the mode of seeing you guys live. Okay, so let me go ahead then, and let me clear that up, and let's work through a couple problems. Okay, so real quick, on your paper, take about a minute. Take about a minute to answer this question here. Okay, so and then I'm sorry. Forget the paper. Just on, don't worry about writing it. Just type in your answer onto Edpuzzle here. Answer number 2 from the problem set here. Okay, so if the equilibrium lies far to the right, okay, what can you say about the value for Ka? Okay, if the equilibrium lies far to the left, what can you say about Ka? And then include in your answer, okay, whether we have then a weak acid or a strong acid. Okay, so go ahead and take about 30 seconds. Type in your answer into the Edpuzzle. Okay, type it into Edpuzzle itself. Okay. All right, let's go ahead and let's take a look at this. Okay, so the equilibrium lies far to the right. Let's go ahead and let's examine what that means. If equilibrium lies far to the right, let's go ahead and take a look at this. That means then that if we look at Ka, that means that the product is going to be favored. Okay, which means then the Ka then for an acid, for example, you're going to have more. The ions, they will be greater than the undissociated acid. Undissociated acid itself. So if Ka lies, if equilibrium lies far to the right, okay, let me exaggerate this really quickly. Let me exaggerate this. So we have then the dissociated ions being present in a much higher concentration than the undissociated acid. Okay, so that means then Ka is going to be and if we take a look at this, it's going to be very big. Okay, so it's going to be large. Okay, it's going to be very big, which means then we have here a strong acid. Okay, so we have then a strong acid, if that's true. So if equilibrium lies far to the right, the acid is very strong, Ka would be very big. Okay? So the opposite then would be true then for if equilibrium lies far to the left. Okay? If equilibrium lies far to the left, we can do this analysis again, okay? And I'll exaggerate the terms here. Okay? That means that in this case, the values, the hydrogen ion concentration, and the hydroxide and the conjugate base is going to be much smaller than concentration of the undissociated acid. Okay? So therefore, in this case, then the Ka is going to be very small. It's going to be small. Whoops, let me go do this here. Okay? Or less than 1. Okay, and which means then we have a weak acid weak acid, a weak acid, when this is the case. So when we can use equilibrium then, folks, to determine whether we have a strong or a weak acid, okay, based on the value for Ka. All right, hopefully you got that, folks. Hopefully you got that. If not, then please make sure you, if you're not quite clear on this, make sure you email me and let me know. Okay. All right, let's do another one. Let's do another one really quickly. Let's take a look at this one here. Okay. We have this particular acid, generic acid. What we do know about this is, what we're told about this then is that water is a better base. Okay, so remember, in this particular, let's go ahead and let's practice some more. Okay, so in this particular reaction, this is our acid. Okay, this is water's function as a base here. This is our conjugate acid. Okay, and this is our conjugate base. Okay, all right. So what they're asking us to do here is they're asking us to take a look at the two bases. Okay, so let's take a look at this base here, our water, and compare it to this base here. That's what they're asking us about this problem here. So they say that water is a better base than the anion. Okay? That means then what this is telling us is then when they say that is water is a stronger base. Okay, water is the stronger base. This is stronger, and this base is weaker. That is what they are telling us in this particular part here. So water is a better base; it's a stronger base than the conjugate base here, the anion. Okay. Do products or reactants dominate at equilibrium? That means then which side of this reaction is favored if water is the stronger base? Understand what we said then. When water is the stronger base, that means that it does a better job of accepting this hydrogen ion than this base. This base doesn't do a very good job of accepting a hydrogen ion from the hydronium here. Okay, so therefore, then, if that is the case, if water does a better job of removing this hydrogen ion, it's going to shift the reaction towards the right. Okay, so the reaction will shift towards the right. Reaction shifts or to the right. It favors if that is the case, then products then will be favored in this particular process. Okay, so the products will be favored. Okay, that means then you're going to form more product. That's what it means then. What will dominate at equilibrium? If the products dominate at equilibrium, that means then we have if reactions shift towards right, towards equilibrium, that means then we have products that are favored. Okay, all right. So what does that say then about the acid itself? Okay, this acid, if the base here is a stronger base, okay, what does it say that if water is a stronger base than this conjugate base here? Okay, now be careful about this. If water is stronger than this base here, what does it tell us about this acid here? Well, remember, if the reaction is going to shift towards the right, if the reaction favors the right-hand side, okay, that means then the dissociation is going to be greater. You're going to have more of this acid dissociating. The more the acid dissociates, then that means that it is a stronger acid. Okay, so it is going to be a strong acid. Okay. We're not saying water is a strong base. We're not saying water is a strong base. Water is not a strong base. It's not a strong base. Okay. What we are saying then is that it is stronger than this base, than this anion here. That's what we're saying. And if water is a stronger base than this anion, what that tells us then is that this acid here is a very strong acid. It's willing, and and water is strong enough to take the hydrogen ion from this acid here, because this acid is already willing to give up that hydrogen ion anyway. Okay? So be careful with these two questions here. Okay? Be careful about that when you answer these questions. Okay? All right, so I think the last question should be pretty straightforward. If we have a strong acid, then we expect then the Ka to be greater than 1. It'd be greater than 1, we should have then a large Ka value. Okay? All right. So again, please email me if you have any questions on that. Okay, so let me ask you then to try this problem here. Okay? All right, let's take a look at this problem here. Okay, so hopefully you got that that sample problem out of the way. But let's take a look at this one really quickly before time runs out. So what we want to be able to do is, and we want to be able to calculate also then for the hydrogen ion concentration. And from that, when we talk about pHs tomorrow, we can determine then the pH of a solution as well. Okay? All right, so we have then a solution that has a hydrogen ion concentration, hydroxide ion concentration of 10 to the minus 5. Okay, so let's go ahead and write this down. Okay? Okay? So we have then a hydroxide ion concentration of 10 to the minus 5. So what we're saying then is the concentration of hydroxide ions here is going to be equal to 1 times 10 to the minus 5 molar. Okay? Can we find the hydrogen ion concentration of this solution? Okay. All right. But we can go ahead then, we can answer this question first. That is this solution neutral, basic, or acidic? Okay, so let's go ahead and let's answer that question really quickly. Okay. All right. So now, first of all, we know that this cannot be neutral. It cannot be neutral here because remember, for a neutral solution, you guys, for a neutral solution, let me go ahead and write it over here for us. Okay, for a neutral solution, okay, for it to be neutral, the concentration of the hydrogen ion has to be equal to the concentration of the hydroxide ion, and both have to be equal to 1 times 10 to the minus 7 molar. This is not 1 times 10 to the minus 7. So you know this cannot be a neutral solution. Okay. All right, for an acidic solution, okay, we said, remember, that the hydroxide, the hydrogen ion concentration has to be greater than 1 times 10 to the minus 7 molar, okay? And the hydroxide ion concentration has to be less than 1 times 10 to the minus 7 molar. This is greater. So we're looking at this here. This is a hydroxide ion concentration that is greater than 10 to the minus 7. 10 to the minus 5 is bigger than 10 to the minus 7. So this cannot be an acidic solution either. Okay? So it has to be a basic solution. But just to summarize, look at our summary here. And so again, you can use this basic summary that I have given you already to determine, before you even do the calculation, whether this solution is acidic, basic, or neutral. Okay? So for a basic solution, the hydrogen ion concentration has to be less than 1 times 10 to the minus 7. We don't have that yet, so we don't know. So we can't say that we can't call this basic, this solution basic, based upon the hydrogen ion concentration, but we do know the hydroxide ion concentration. Okay? And it is greater than 10 to the minus 7 molar. 10 to the minus 5 is greater than 10 to the minus 7. So that's why we know then that this solution is going to be basic. Okay? Use these summaries here to help you determine the whether a solution is going to be neutral, acidic, or basic. Okay? So that you can answer before you do any calculation, okay, based upon what you know about the concentrations of the hydrogen ion and hydroxide ion concentration when they're neutral. So 10 to the minus 7, that's kind of be the number that you got to keep in mind. Okay. So I'm out of time here. So what we will do tomorrow, okay, is now based on now that we know that this solution is basic, we have the concentration of we're given the concentration of the hydroxide ion. Can we then calculate for the concentration of the hydrogen ion? And the answer hopefully is yes. Hopefully you can recognize that because we do know this, that we know then that the concentration of both of those, whatever they may be, has to equal 1 times 10 to the minus 14. And based on this here, and then after this is just plug and chug, substituting it in, you can solve then for the hydrogen ion concentration. Okay, and so this calculation ends up being very, very simple, folks. Okay, and so what we'll do then is tomorrow, I'll pick up right here. I'll work out this problem for us. Okay, and then I'm going to give you a chance to practice doing these calculations and answer more conceptual questions about acid-base solutions. Okay, all right, very good, folks. Please make sure you email me your questions and let me know what questions you have, and then I'll answer them. I'll check the questions and I'll answer them in tomorrow's video. Okay? All right. Have a good day, folks, and I will see you tomorrow.